All right, welcome everyone. Today we're going to be talking about pushing Kubernetes to the limit when it comes to performance, specifically throughput and then latency. Now, this talk is going to be kind of jumping across different resource types and subjects, and that's largely because when it comes to kind of high performance, there's kind of these fundamental properties, and some of those properties live both in your code and in the cloud providers and also inside of Kubernetes. So while the subject is Kubernetes, we're going to kind of be like flipping across these different domains and then kind of bringing it back into Kubernetes and some of the settings that you need there to actually push your workloads. Because you kind of have to fundamentally understand what you're doing at a core level, whether that abstraction is provided by Kubernetes, your programming language, or your cloud provider. So here's an overview of the agenda today. Basically, we're going to give our intros and kind of tell you why you should be trusting us and listening to us, why we're the ones talking about this. Then we're going to talk about the significance of like why you care about low latency or high throughput workloads on Kubernetes. Then we're going to go through the high throughput one first. Frederic's going to cover that content. It's going to be largely talking about a use case, and object storage, networking, and disk I/O are going to be kind of the focus there. Then I'm going to talk about low latency, so specifically trying to deliver things within a few millisecond window. And that's going to focus largely on memory and CPU. So, who are we? I'm Jimmy Zelinskie. I'm a co-founder of a company called AuthZed. AuthZed built a product called SpiceDB, which is a database service built specifically for storing and querying authorization data. So that is a low latency system, and we run our products all on top of Kubernetes and support our customer environments all on top of Kubernetes. Prior to that, I basically have been in the cloud native space since the beginning. Before the CNCF was even created. I've created a couple of projects in the space, like the operator framework, and I've committed code to a bunch of foundational projects in the cloud native ecosystem. I'm also an OCI maintainer. Frederic?
Jimmy and I know each other from CoreOS, so we both kind of started around the same time. I'm the founder of a company called Polar Signals. Our product is a continuous profiling product, which essentially allows you to understand performance characteristics of your workloads down to the source code. And our system, in contrast to AuthZed's, is more of a high throughput system rather than a super low latency one. So that's why I'm focusing on that part. You may also know me through my work on the Prometheus projects. I'm a maintainer of the Prometheus project. I also created the Prometheus operator. If people are using maybe Prometheus on Kubernetes, you're maybe using some of those things as well as a Tanos maintainer.
All right, you may have seen a visual something like this. This is a representation of Jeff Dean's kind of latency numbers. Basically, if you're not familiar, Jeff Dean is like the head researcher at Google. He's been there for many years. He's basically championed a lot of the papers and foundational technologies that you've seen come out of Google, especially when it comes to the cloud software and how they've scaled their business and all the backends associated with it. This is just my favorite rendition of it because you can curl a very short URL and render this in any terminal. So if you're like, hey, hold up, wait a second, what is the latency for like decompressing something with Snappy? You can just like curl this really quick and then have like a ballpark idea of how it compares. The utility of this visual, I guess, is the real question. Like, why does Jeff Dean think that all programmers should have like a good understanding of kind of like these comparisons between latency? I think that is the same reason why this talk matters to this audience. Did you want to go over these 3 bullet points, Frederic?
Yeah, so basically, performance matters for essentially one of those 3 reasons. The most important one, and this is sort of the domain that Jimmy and I move in, fundamentally some problems require high throughput and or low latency to be solved at all, to work at all. But there may be other reasons why you want to improve performance of your system, and cost savings is certainly one of those. I think everybody likes the idea of doing the same work and spending less on that. And then ultimately, if we do less, often that results in simpler systems and ultimately then reducing the operational burden of operating those systems, which is also a property that I think everyone likes about systems. So yeah, Let's dive into high throughput systems. And for that, I brought an example today of a cache that it sits in front of object storage. I think this is kind of an architecture that is becoming more and more important and more popular. You may have seen earlier, I'm also a maintainer of the Tanos project, which is kind of a distributed version of Prometheus, if you're not familiar with it. It also stores the raw data on object storage. And so again, this is kind of becoming more and more popular. And so oftentimes people want to, for various reasons, and we'll see which reasons a cache in front of object storage actually makes sense once we understand the fundamental nature and physics between these systems. So in our case at Polar Signals, the reason why caching of object storage data matters is because we run pretty heavy queries against a large amount of data that ultimately rests on object storage, but of course we want to make it as cheap and as fast as possible to query this data and make it available to be interactively explored by our users. And so this is kind of the example, this cache in the middle is what I'm going to go through and analyze the fundamental properties of, so that we understand what we get out of a cache and when we should be applying this kind of architecture. So a bit of napkin math here. This is a little bit small, so I'll go through it. So basically, for every request that you do against object storage, ignoring the cache for a second here, we pay a baseline 200 milliseconds of latency. So every request, kind of the P99 latency is 200 milliseconds. And so this is a fundamental factor why caching may be really desirable. If these 200 milliseconds matter to us and we want to remove these 200 milliseconds, then caching could be really interesting. Something that's quite interesting and something that we can rely on from our cloud providers is there's basically no throughput limits in terms of object storage as long as we have the network bandwidth on our network cards. And so this is actually a really interesting property and one that we're going to be making use of a lot with this cache. Roughly what AWS and GCP are telling us, for each request that you do against object storage, you'll get about 100 megabytes per second of throughput, provided that you still have enough bandwidth available on your network card to actually do this. The recommended chunk size, so when we have data at rest on object storage, the recommendation from AWS and Google and Azure are to chunk each of these requests. If we're, let's say, requesting a 1 gigabyte file, chunk them into 8 megabyte slices. That way you can achieve the highest throughput. However, something that we also need to be aware of with object storage is every single request that we do does cost. However, the cost is actually pretty low, which is ultimately why this kind of architecture is really desirable. We pay about 400ths of a cent for 1,000 reads. And so a very quick example of napkin math here, if we do actually want to request a 1 gigabyte size file, we can chunk that up in 128 requests, each of 8 megabyte size. And that costs us the 200 millisecond base latency plus 125 milliseconds to actually retrieve all of those chunks. That ultimately ends up costing us 1/100th of a cent. So this is kind of a base number that we're going to be using throughout this example talk, and why some things matter and why some things don't matter. So I already kind of started hinting at this. This ultimately only truly works if we have 100 gigabits of network available. That does exist on cloud providers, but you would need to be careful, and we'll see this later, which instances you're actually choosing. So this kind of illusion that cloud providers have given us that you don't need to care about the underlying hardware and all of this is fundamentally false when you're thinking about high performance and low latency applications. You actually do need to care quite a big to quite a large degree what the capabilities are of the underlying instances, and you need to be careful with selecting those. So to get exactly the properties that we just talked about, you need 100 gigabits of networking. And every time we have that, and we'll see in a moment which instances which instances this applies to, every time we have the network bandwidth, our latency doubles. So that's really important for low latency, for high throughput. On AWS, for example, some of the cheapest instances have only 5 gigabits, but it can go all the way up to 400 gigabits with the P4D instances. On GCP, we start a little bit higher, but we also top out a little bit earlier with their GPU instances, the A3 and G2 instances. The C4s are actually really interesting, particularly the C4A. Google has finally caught up a little bit in terms of the ARM64 game, which I think AWS has kind of been largely pioneering, I would say, in the cloud ecosystem. But the C4A instances are now super interesting for high throughput as well. So in case you can't read that, the C4A ones are the ones with 100 gigabits, and they're pretty good in terms of price per performance, both in terms of CPU, memory, and networking. So again, if we have this example of reading 1 gigabyte, ultimately, at some point, this has to be retrieved from object storage. If it's at rest there, we're always going to pay the 200 milliseconds of latency plus 125 milliseconds in actually retrieving this content. Now, between, in our case at Polar Signals, our query infrastructure and the actual cache, let's assume for a second that we're going to have 100% cache hits. We are still going to be paying 125 milliseconds in latency. And so this is actually a really important piece of data to understand, because it influences what other things actually matter. Because, for example, a reality check in networking on cloud providers is everything that I've told you so far kind of ignores the fact that we are living in the real world and we have multiple zones in a region. If you're not familiar with this, basically each zone in a region on a cloud provider, they are dedicated data centers and are typically anywhere between 20 to 100 kilometers physically apart from each other. They are very, very well connected to each other with high-speed network connections, but we are still bound to the laws of physics. And let's take the example of data centers that are 100 kilometers apart from each other. We're still working with a base latency of 0.33 milliseconds. So that is assuming that there's no delay because of networking hardware or whatever. We cannot get faster than 0.33 milliseconds of latency between those zones. Obviously, the distance matters because speed of light, but that's what we'll work with for a second here. And so what that means for our example of high throughput, this kind of latency across zones doesn't matter. For some very low latency applications, it may matter because, as we're seeing here, I have a couple of examples of latency numbers. So within the same zone, within the same data center, we are definitely sub-millisecond, whereas across zones, we're somewhere in the realm of up to 2 milliseconds. In our example, we're always going to be paying 125 milliseconds of latency to retrieve 1 gigabyte of data. 2 milliseconds doesn't really matter. The big chunk is still how much network throughput can we actually push through the network cards, right? So this kind of latency, for our case, doesn't matter, but for other kinds of cases, may actually matter. For us, what matters much more is the cost of network bandwidth across the zone. That costs us 1 cent per gigabyte transferred. And so this fundamentally governs how we're going to be thinking about caching of object storage data. because the really the most important part here in the equation is the cost of network traffic. Within the same zone, we get effectively the throughput of our network card, and then the rule of thumb for cross-zone traffic is about 5 to 20% penalty, but in the grand scheme of things, not extremely huge. Your mileage may vary pretty significantly across cloud providers. It's pretty hard to see, I think, but the scale, the speed of light for AWS and GCP is clearly faster than for Azure. I don't know exactly what's up with that, but yeah, I don't know. The speed of light for Azure is about apparently half as fast. So yeah, if latency is actually what matters to you across zones, these kinds of data points do actually matter to you. So again, if we are always going to be paying 125 milliseconds in latency for getting our data through the network, then this kind of path across a zone for latency doesn't matter. However, in terms of cost, it certainly does matter. If we have a cache miss within the same zone, we're paying 1/100th of a cent in object storage calls, whereas for cross-zone traffic, we're paying 1 cent, which is 100 times more expensive. And so this is exactly for this type of workload, something we want to avoid at all cost. And so at Polar Signals, the way that we solve this is that we just encourage network traffic to never leave the zone. Now, there are various ways of encouraging this. There are features directly built into Kubernetes to encourage this. Up until, I'm forgetting the version number at the moment, but up until recently, this was done using topology-aware routing. And the auto mode essentially tried to load balance the traffic evenly across zones, but try to encourage it within the same zone. But there were kind of some sort of unpredictable features of tying network traffic to available CPUs, that this didn't become a particularly ergonomic feature. And so ultimately this encouraged the new evolution of what's now called traffic distribution, which essentially is just if there is a network endpoint available within the zone of where the outgoing workload is, then I'm going to route it to that endpoint that is within the same zone. Only if there is no endpoint available would it route the traffic to a different zone. And so I think this feature is probably going to become much more widely adopted, but it is a brand new feature as of Kubernetes 1.31. And so the configuration here, in case it's hard to see, is traffic distribution prefer close. So Kubernetes 1.31, traffic distribution prefer close, and your CNI provider actually has to support it. So that is one way to do it. And then the most naive way, and sometimes actually a really good way to do this, is to literally set up your stack multiple times, once per zone, and only genuinely allow ever routing that those requests within components that are within the same zone by literally having a service per zone. So yeah, but configuration is good, measuring it is better, and so due to lack of having good metrics available for this type of thing from cloud providers, we actually created a project called KubeSonnet at Polar Signals that allows us to measure exactly which workloads are causing cross-zone traffic, because that's a major cost driver for Polar Signals. And so whenever, now that we've gone through this exercise of actually optimizing our workloads to never cross the zone boundary, we can now use this for alerting purposes, for example, to make sure that if we're accidentally doing something that's causing cross-zone traffic, we're catching it early rather than when our cloud bill gets too large. Last but not least, disk also matters. So far, we've kind of assumed that everything is just zero latency and all in memory. Memory speed is much higher than network throughput. Disks, if you wanted to also kind of store all of the cached data on a local disk, let's say on a local SSD, that's a popular way to do this with object storage data. Then there's actually a really important piece of information that we need to know about, which is each of these SSDs that are attached to our instances on a cloud provider, each of them can only do 660 megabytes per second. And so this is, we need to have a pretty large RAID array of disks to actually match our 100 gigabits of network traffic, of network card that we have available that we used as our example. And so depending on the SSD available, that may be anywhere between 14 to 24 local SSDs that you would need to attach to your local to your nodes on GCP, for example, to match those 100 gigabits. And so all of these calculations are really important to do so that we don't have kind of unexpected behavior when it actually comes to running our workloads in the real world. So, oh, sorry, we got the order wrong here. The way to do this on Kubernetes is we can use this feature called local ephemeral storage. On GKE, for example, this is a managed feature where you can basically just say, I want all empty dir volumes that I'm going to be mounting into my containers on nodes that have local SSDs mounted. I want those to actually use the local SSD. And so we can then use just the ephemeral storage requests on our containers and limits to actually do those requests against the real local SSDs. And that way, we can actually tie this back into Kubernetes. We can also use the mtdir size limit to ultimately limit this. My general recommendation is keep the request, the limit, and the size limit the same. Otherwise, it gets kind of complicated to actually consistently manage across your entire infrastructure. So yeah, we'll flip back and forth a little bit here. Sorry about that. So now we've gone through an example of high throughput. What about low latency?
We've only got a couple minutes left, so I'm going to try to fly through this. So if you think about kind of the first image I showed, Jeff Dean's numbers, that comparison, and you're trying to target a low latency workload, like your workload has to be constantly delivered to the end user within a certain time boundary. That time boundary might be single-digit milliseconds. The first place you probably want to look is your programming language, and that's just because garbage collectors can span their pause times from nanoseconds all the way up to seconds, depending on what you're doing in the language. And if you're doing something high throughput, it probably means, low latency, you're probably also trying to serve a lot of people at the same time, which means you're churning through lots of memory, which means there's lots of garbage being produced. So you're gonna have to fundamentally think about your garbage collector if you're writing a garbage collected language. And now fundamentally, garbage collectors kind of are this trade-off that you're always making, and that trade-off is throughput for latency. So to do that, you kind of have a couple different knobs you can use to kind of work in tandem or give hints to the garbage collector to help you actually get the performance that you're trying to achieve. The first is just fundamentally reducing allocations. And you can just do that by pre-allocating things. So making sure that you're not making a bunch of tiny, small individual allocations, which are going to add up to a bunch of different things now the garbage collector has to track. Rather, you can kind of pre-allocate one large thing at the beginning. There's a couple different strategies you can use there, like things like arenas. The real big one that I honestly see being a huge boon is allocation reuse. If you open up pull requests to like a community library and you just fix a couple allocation reuses, sometimes I've seen like massive performance improvements just like hit the whole community at once. Saving allocations in something like gRPC is just going to impact the entire community, and you might see throughput numbers like double or even triple just from a tiny pull request just reusing memory. Actually, LinkedIn did that pretty recently, if you're interested in gRPC specifically. So there's also different allocation schemes. I kind of mentioned arenas earlier when it came to pre-allocation. Another thing you could do is fundamentally design your software a different way. One strategy would be thread per core. This is kind of how certain databases like SiloDB work. What they do is they actually design it such that requests come in, they get dispatched to one particular core, and then that core runs the end-to-end lifecycle of that request. Unlike a lot of other programming languages where you're kind of context switching in between and you're kind of managing, any core could be touching a particular workload. In this scenario, you know end to end that this request was processed by this core and then the next request came in serially to that core. So instead of kind of like switching between a bunch of different tasks, you kind of have these separate pipelines. And those pipelines then scale as you add more cores. The next thing is avoiding memory pressure. So you can just use GC-friendly types. I'm going to give an example of that after this. And then fundamentally just tuning the GC, giving the GC details about the environment so that it knows when it should be running, so it's not running the garbage collection process more often than it needs to. Cool. So I have this example of Go garbage collection. And the question here is how much time does GCing the code on the top take? Well, the answer is ON. It has to actually iterate over every item in the map. And that is because the user struct has a pointer in it. So the garbage collector needs to go through every single item in the map and then chase down all the pointers in every single item to know if it has hit a root or not. Hit a leaf or not. So if you were kind of storing session IDs to users, which I have as this example, one cool trick you could have is just storing session IDs straight to usernames. Say I only needed the name field. I didn't actually really care about the profile pointer. I could actually have a separate map, and while it would consume more memory, the GC time for the second, like the lower version of the code, is actually 01. The garbage collector can actually entirely skip iterating over any items in this map because it knows the native types to this are int and string. There's no pointers to chase, so it doesn't actually have to do any work. All right, so I kind of wanted to transition to talking about Kubernetes features that would actually help you achieve kind of these things once you've designed your software to be memory efficient. The Kubernetes defaults, I like to say, is like your kind of like router password. The defaults are basically like, it's best effort, it kind of works like, I'm sure if you look at the Wi-Fi right now, you'll see there's a bunch of people running default networks. You don't really know the password. It's not really secure, though. That's kind of what the Kubernetes defaults are like. There's really no protection about any other pod consuming all the memory on your node if you haven't tweaked anything. You don't get quality of service. And then, like, if you have two sensitive workloads, they could still get actually scheduled on the same node. So that means if that node dies, like, you actually lost 2 of your pods rather than 1. So the thing that everyone is going to tell you is, cool, just slap some requests and limits onto things. If you're unfamiliar, requests basically tell Kubernetes what must be available for something to get scheduled, and limits kind of like set a hard limit, and the killer actually will kill it once you kind of exceed those boundaries. The problem with this is it's actually reactive and not proactive. So what happens is the Kubernetes scheduler is actually going to ping every so often and check. And it's actually an API flag how often you're going to check to see if these pods are exceeding that boundary. The problem is there's actually a minimum value here. And the minimum value here, I can't remember what it is off the top of my head, but it's like a second. It's not milliseconds, right? And your workload is probably handling hundreds or thousands of requests per second. So that means in the time it takes for Kubernetes to react to something bursting on a particular node, you could have just flubbed thousands of requests. So that's not really acceptable for a lot of workloads. Then the other neat thing that you can do here, I haven't actually seen a lot of people talk about this. When you set these limits, so say you set a memory limit here, you can actually reference that memory limit using the downward API and pass that into your applications. Specifically, this is useful for garbage collected languages like Go or Java, because then you can actually tell that environment, hey, like you have this much memory, which means the garbage collector will be aware when you're getting pressed up against that memory limit, and it will actively run in tandem and work better with your environment. Cool. So once you kind of cover the memory side, you can start thinking about CPU. Once again, the most important thing here is kind of the design of your program. Ideally, you want to parallelize your core algorithm because fundamentally, like CPUs don't get faster. We just get more cores and kind of more clever architectures around sharing. So you're going to have to do that. The next thing you can do is kind of take that parallelism and think about it not just on a per node basis, but on a like cluster-wide basis. So the example I have here is SpiceDB. SpiceDB actually does a thing where when it serves a request, it breaks it down into sub-requests, and those sub-requests use a consistent hash to associate where the sub-request will be routed to in the overall cluster. And then basically that work is identified by the actual kind of work being done in the consistent hash ring, and then we kind of cache those values in the cluster at that location. That way you kind of think of it as like a distributed cache storing thunks of partially evaluated results. So if you have any structural sharing across your requests, you can actually reuse that work. There's a couple other strategies here, things like function called deduplication. That means if two things actually are trying to do the same work, you can actually use a mutex to stop the second one from running until the first one returns, and then you use that result to return to both, which will cut the latency for the second one in half or more. The next thing you can do is actually build a scheduling system. Go, for example, and Java don't actually have ways to build priority around the default async framework, so you kind of have to build those yourself. The next thing you can do is just hedge. So if a request comes in, you can actually double the work, because if one of them breaks or fails, you need the other one to come back in time. The next thing here is like runtime diagnosis. You really have to profile to understand the stuff. There's no intuition. You're not going to like just understand from writing the code how it's going to perform. You have to measure, and measure in a real environment. Basically, all your time is going to be spent actually bookkeeping, probably not in your core algorithm. So things, you could use SIM in a bunch of places, but most likely you have to worry more so about noisy neighbors. So at a high level, if you're unfamiliar, there's context switching. That is going to be your killer here. Basically, your machine, there's parallelism and concurrency. You're probably doing a lot of concurrency, swapping between different tasks. What you really need to do is prevent this from happening, because this is happening actually at a bunch of different layers. Happens in your programming language, then it happens at Linux. Linux is swapping your process with other processes on the hardware, and then if you're using a CPU that has hyperthreading, for example, your CPU process actually is swapping between the actual physical core. It has hyperthreads that it's scheduling across a single core. Every single one of those context switches at any of those layers is adding overhead and blowing away caches that are going to impact your performance. So there's one kind of like major Kubernetes thing you can use here, which is taints and tolerations. That basically lets you pin your workloads to specific cores, and you can kind of set labels to the policies around that. That's going to guarantee you that like you at least land on a machine that has hardware optimized for your workload. Then there's this super obscure feature, which is static CPU manager. This one lets you actually specify a whole number CPU, and if you do that, you don't give it like part of a CPU core, it will actually pin those cores. And you can actually use this to say, actually, I want 0 other processes running on these cores ever on this node. This is super useful because you actually get that guarantee, but you are trading off one core that has to run the system. All right, try to make it really quick, but I hope you learned something in this talk, and then I hope you get excited and go look at your programs and get ideas for how to speed them up. Cool. Thanks, everyone.